All right, here we go. Chapter 13 is all about having polynomials that have more than two solutions, where those more than two solutions are all like random numbers. Also having rational and even complex solutions. And it's really a key for this chapter of don't make tiny, stupid mistakes. If you make tiny, stupid mistakes, you will get the answer wrong, and it's very easy on this chapter to make tiny, stupid mistakes. So let's begin with this problem. It says we need to solve for x. X cubed plus x squared minus 11x minus 15 is equal to 0. And then it gives us one root, saying that one root is equal to -3. So we're going to solve this both with long division and with synthetic division. I'll describe what this is later, because if this is a new chapter to you, you have no idea what synthetic division means. And then long division with a polynomial also seems very convoluted. So let's just begin with the long division. First of all, we have to think, what do we need to divide this by? Well, if it gives us one root, we know that a normal function, any function given, is equal to one of its roots, so it would be x minus that root, times some other some other, I'm going to call it d of x, that would equal it. So basically, obviously, if we divide f of x by x minus r, we'll get d of x. And if we notice here, this x minus r only has a multiplicity of 1. This function initial would be r3, so it would have a 3. And then this d of x would be then with the greatest term x squared, which is perfect because we know already how to solve quadratics. So first what we have to do is find this root in which we divide by f of x to try to get that last dx so that we can continue to simplify everything down. Well, it already gives us that root. It's -3. Don't immediately go like this and then try to say that that's it and that's equal to our root, because that's wrong. If we were to plug in -3 here, we would get -6, not 0. So this has to be a plus. So it's the opposite of the sign of the root it gives us. So that's what we're going to divide by, x plus 3. So we're going to put x plus 3 on the outside, and then our whole thing on the inside. Okay? And now we will just go ahead and solve. Let's look at our first two terms here. We have an x and an x cubed. What do we need to multiply our x by to get it to equal x cubed? We need to multiply it by x squared. So we will then multiply both of these terms by x squared and then do our subtraction as if it were normal long division without variables. So x times x squared is x cubed. Don't bother to try to shortcut it by saying negative x squared, because you'll see later that that will not work. And then we will multiply this 3, so we'll have plus 3x squared. And then we will subtract, and then I put parentheses there to remember to distribute that negative, because if you don't distribute that negative to the other signs that we have and you only do it to the first one, that's one tiny mistake you can make. So obviously this is going to be 0, hence why we multiply by x squared. The first term is always going to cancel out to be 0. So then we're going to have x squared plus -3x squared, which would be -2x squared, minus 11x minus 15. Okay, and then now we'll find what number should we multiply here. We should do -2x, because that would give us -2x squared when multiplied by x. So -2x squared, multiply by this one, -6x. Let's not erase the other parts. And then this is a subtraction here, so that will be equal to 0. This one will be positive 6x, so add that, we get -5x minus 15. Multiply this over, -5 is what we should multiply this by, so -5x minus 15. When we subtract this all, it gives us 0. Now, we will know that we did our math wrong if we don't get 0 as a remainder here, because it gives us the fact that it's a root of -3. And all roots, when divided by their initial polynomial, will not have a remainder. If they have a remainder, it means it's either not a root or you did your division wrong. But it gave us that was a root, so obviously we should get that. And that's another way you can verify if roots are roots, by just going by long division, even though it's super long and convoluted. Going by long division, if your remainder is 0, then you have a root with you. If not, you don't. So this is what we want up here. Our dx that I was talking about earlier, our remainder, is x squared minus 2x minus 5. So that's very convenient, because then that means that this times this is equal to our initial function. Okay? And then now we want to solve for what this one is. So this one here, if you'll notice, can't be solved any way other than the quadratic formula. We can't try to split this up and factor it normally. So let's just go quadratic formula. X is equal to 2 plus or minus rad 4 minus 4 times negative 5. And then we will put this all over 2. So then we'll have x is equal to 2 plus or minus the square root of 4 plus 20. So 24 over 2. We'll pull out a 4 from that 24. X is equal to, and then divide everything by 2 in the same step. 1 plus or minus, we pull out that 2, so we divide the 24 by 4. And then we get 6. So 1 plus or minus rad 6. Keep in mind we're doing a plus or minus here, so there are actually 2 roots here, which means that our roots are 1 plus or minus rad 6, and then also the root it gives us, negative 3. So these are our roots. Now let's solve this by synthetic division. I'll tell you, this step here where we use quadratic formula will be the same with synthetic division. So synthetic division is basically skipping all of this long work. So how we're going to set this up is by putting our root at the top. We want the root to be that r number. So if our root is negative 3, we want positive 3 to be up here. Or no, we want this to be our r number, so this has to be negative 3. So you actually have to put the real root up there. Now I'm going to draw a dash like this, because this is how you set up synthetic division. You put one number in the box up here, similar to this over here, and then you put all the coefficients of all the numbers out here. So we would go 1, 1, negative 11, negative 15. So then what we would do is this here is an addition bar. So we have a 0 here, so it would drop straight down as a 1. Then we would multiply it by this negative 3. So negative 3 times 1 is negative 3, and then that goes in the bottom bar of the next column. Then we add it over, we get negative 2, multiply it here, we get 6. So this here would add to negative 5, multiply here, we get 15, 0. And then all of these are our coefficients of x squared, x, and then 0x, and then this would be our remainder. So that means we have now x squared minus 2x minus 5, which is exactly what we did over here, but it's way quicker than all this nonsense work. And then we would just go through quadratic formula with that again. So that's how we would solve for number 2. Now let's go through and do number 3. And that's all it was asking for, right? Yeah, that's all it was asking for. You can see it fine. Yes, you can. Okay. 3 lists the possibilities for the rational roots of the equation. So possible roots of 2x to the 5th minus 4x to the 3rd plus x minus 6 is equal to 0. So we need to find the possible roots of this. So when we get asked the question of possible roots, that means that we want to look for how many positive roots there are, how many negative roots there are, and then how many, if there are, complex roots there are. So I'm going to explain how this works in just a minute. I'm going to solve it using what's called Descartes' rule of signs, and then explain why these certain rules exist, because there are rules of Descartes' rule of signs that don't make sense unless you take a minute to think about it. So we have our possible roots of this here. So what we have to do first in order to solve for Descartes' rule of signs is think about how many sign changes there are. So this here is our normal f of x. So we have to think of how many sign changes are there on just the f of x where it's a positive x. We start at positive, go negative, so that's 1, go positive, so that's 2, go negative, so that's 3. So we will have 3 in the positive. So that means that we will have a positive fx, and then this here will have f negative x. So really quickly, just to make it a bit nicer, we're going to have positive x there. And then f of negative x, what we'll do is we will plug in a negative x for every single x here. So if we plug in a negative x for x squared or any term that has an even number being multiplied, it'll equal the same thing. Although if we plug it in for any odd number, it'll then be equal to negative x cubed. So we can know that there, and then know that if we were to plug this in for negatives, you would get negative 2x fifth, plus 4x cubed minus x, and then this one wouldn't change because there's no difference to when we plug it in there. So that would be our negative f of x. So let's think of how many sign changes. 1 change, 2 change, no change. So just 2 changes. Okay, and then we have 5 possible roots total, but it wants us to classify them. So now we have to think of if there are any complex roots. But first what we'll do is realize for a minute that this isn't all the combinations we can have. So we can also have 1 and also have 0. Now, why is because we'll go down by pairs of 2. If we think for a minute, there are times where if we have a 3 or a 1, if we just have, like, let's think of our last problem. Our last problem had this, x cubed plus x squared minus 11x minus 15 is equal to 0. Now, we knew that our roots were negative 3, 1 plus rad 6, 1 minus rad 6. So we know that integer numbers can come solo. They can be solo. So that means that there is one solo integer number for a positive here in this possible one here. Now, these two are rational roots. So this would be a rational positive root. This would be a rational negative root, because when you actually solve this out, it would be something along the lines of like 1 point, or it'd be like 2 point something. And then this here would be like negative 0 point something, if we were to actually put that into a calculator. So here we have rational roots, and then notice that all the rationals will come in pairs of positive and negative, which means that if we have a positive here that's a 3, if it comes as a rational pair at all, we can subtract those out, and then that could be our possible positive as well, which means that we either do or don't have these. So we will subtract out by the number 2. Now, same with the negative one, that same rule applies here, and then our rule for these complex numbers also applies, because there's a chance where, let's just say for a second, let's say the roots of this were 3, and then we have 1 plus rad 6i, and then 1 minus rad 6i, and this is just interpolating as if this were instead a different number, and we got if you notice from the other problem, a 2 plus or minus negative 24 over 2 as what we got in our quadratic formula. This would give us the exact same thing as with these i's here. So the i's, all the complex roots, also come in conjugate pairs, and that's called conjugate pairs when they come in pairs like that. So that means we can either have 0, 2, or 4, because there's a possible of 5. So our actual pairs here, if we wanted to go positive, negative, and then I, would be something along the lines of, we could have 3 positive, 2 negative. We could have 3 positive, 2 complex. We could have 1 positive, 2 negative, 2 complex. We could have 1 positive, 0 negative, or let's just put all of the things here. So 0i, this will be 2i, or actually 0. 0, negative, 2i, just so that we can have everything evened out. And then here we could have 4i. So as you see here, our possibilities are quite a lot. And I believe there's another one. We've gone 3, 2, 0. We've gone 3, 0, 2. We've gone 1, 2, 2. We've gone 1, 0, 4. Yeah, that is all of our possibilities. So these are all of our possible roots, and that would be the answer. So if you'll notice, the reason why we can decrease each of these by 2 is because rational numbers, positive and negative, and complex numbers come in conjugate root pairs. So therefore, we can decrease it by that much. And that's just as if it weren't able to be solved by that. So as you do more of these problems, you'll note that that is how Descartes' rule of signs works. And what's really cool is that you can figure that out without actually having to go through any solutions. Okay? All right, number 4. I kind of like number 4 because it takes a little bit of abstract thought. So all quadratics in simplified root form, just before we even read the thing, all quadratics in simplified root form will follow the example of this. 0 is equal to x minus r1, x minus r2, times some constant that I will name c. So it says find a quadratic with the zeros -1 and 8 with a y-intercept of -24. So first of all, this seems complicated, but first we know that our zeros are -1 and 8. So let's plug these in for our r1s. So we're going to have 0 is equal to, or rather 0, but also f of x, whatever. I'm going to call it 0 for now because it wants us to find these with zeros. So we would plug in an x plus 1, because that would mean our 0 is -1, and an x minus 8, because that would mean our 0 is 8, and then multiplied by some constant c. It wants us to have a y-intercept of -24. So we know that whatever these two numbers will be multiplied by is going to be the number on the very end, and we know that the number on the very end is the y-intercept. So we're going to set this c equal to a number that would make it equal to 24. Well, 1 times -8 is -8, times 3 is -24. So that means we're going to set our c value equal to 3. So now we're going to say 0 is equal to, let's just multiply everything out, x squared plus, so x squared plus 1, -8, so that would be -7x minus 8 times everything by 3. So that would mean our function f of x is equal to 3x squared minus 21x minus 24. And then let's plug this into our graphing calculator just to make sure that everything does check out. 3x squared minus 21x minus 24. Let's graph. There's our -1, there's our 8, and let's find our y-intercept. So at x equals 0, there it is, -24, perfect. So this here would be our answer. Now we're going to do number 7. And number 7 says x cubed minus 2x squared minus 1 is equal to 0, has one positive root. Use the upper and lower bounds theorem to determine the upper bound and also locate the root between successive tenths. So first of all, upper and lower bounds theorem only can work. We can only go through this when we know what roots there are. And we have a clever trick we can use immediately to figure out what possible positive and negative integer roots there can be. We can take all of the factors of last term, well, the factors of y-intercept is the word I'm going to use. Factors of the y-intercept divided by factors of coefficient of first term is equal to, and then this is a plus or minus, all possible all possible integer roots. So it's important that this mentions that it's one positive root, because if it said if it was anything an even number, then it could have been a rational root, because rational roots come in conjugate pairs. So it's important that this says this has one positive root, which means it has to be an integer, because only integers can come in odd numbers. So now we can use this theorem here to find what possible roots there are. Well, first of all, the factors of the first y-intercept are going to be 1, and then this is going to be positive and negative, divided by our 1 over here, positive and negative. So that means that our only possible roots are positive and negative 1. Now, if, of course, this were to be like a 2 instead, we would have positive, negative, the set of 1 and 2, because it would be all of the factors of 2 divided by positive, negative, all 1, which would mean that it would be positive, negative 1 and positive, negative 2, and then you would keep on going down the list. And I use these braces to mean set. So our only roots here are positive and negative 1. So now we'll use the upper and lower bounds theorem to determine the upper bound. So the upper and lower bounds theorem only works when you use synthetic division. So let's try to synthetic divide. We know that the possible integer roots are positive and negative 1. We want to determine the upper bound, so we're going to start with our positive stuff. The only one we need to use is the number 1. So we're going to put the number 1 up here. We're going to have 1, negative 2, 0, negative 1. Remember that 0, otherwise you will miss it, because that 0 is where the x to the first power is, but there is none here. And then we will solve for this here. Here's our plus sign, drop that 1 down, multiply. Here we have a negative 1, negative 1, negative 1, negative 1, negative 2. So we know now that 1 is not it. Now, of course, we could stop here and say that this here, it's not a positive root, but we want to keep going because we want to see what that upper bound is. So what we're going to do is continue on. Let's try a 2. We know it can't be 2, but let's just use it to figure out what that upper and lower bound could be. So 2, we would go 1, negative 2, 0, negative 1, 1, 2, 0, 2, or no, this would be 0, 0, 0, negative 1. So we have a negative here, which means we're not yet at our upper bound. So our upper bound is classified for when all of our answers are positive. That's an upper bound. We know it's a lower bound when this repeats between negatives and positives. That's how we know it's a lower bound. Now, zeros don't count as positive or negative, so they will differ. So now let's try a 3 to see what we can find for that one. So if we now put 3 here, we'll go 1, 3, 1, 3, 3, 9, and then we have 8. So here is our upper bound. So 3 is our upper bound, and then we want to locate this root between successive tenths. So a very cool thing about how these will work is that if you can't, like, let me draw a little graph to visualize this. So we know that this function will probably do something like this. It's going to turn twice, because we always will turn one less than the total degree of the function. So let's just say it'll start here, go to negative 1, and then turn like that. So we know that at every single root, it will start negative, become positive, start positive, become negative, start negative, become positive. So after and before every root, we will see different, whether or not they are positive or negative numbers. So we can then use this little rule about functions to try to solve where the root is between successive tenths. So we know that 3 is our upper boundary. So let's start at 3 and work our way downwards. So let's plug it into our calculator. So we'll start 3 cubed minus 2, 3 squared minus 1 is equal to 8. So that is a positive number. So now let's go 2.9, since it wants us to do this by successive tenths. And this is just a matter of knowing how your calculator works. That's a 6, so let's go even lower to 2.8 because we're still in positives. So we are going down by only a little bit each time. So let's make this an even more drastic drop to 2.6. We're at 3 now. Let's go 2.5. Okay, we're at 2. We're close. Let's try 2.4 because I don't want to go all the way to 3 yet. Okay, now we can try 3 because if this one's negative, we wouldn't know if it's between 4 or 5. Nope, it's not negative. So now let's go 2.2. Okay, there's our negative. So that means that this one is in between 2.2 and 2.3. So we will write this like this. 2.2 is less than our root, which is less than 2.3. And that is how we can solve for it. Now, and I would just like to note too, this rule about how we can clarify what factors could and couldn't be there, we normally use this when we're trying to solve for upper bounds and lower bounds theorem. And it's a good rule to know for if you're trying to solve for all possible roots. But for this instance, we didn't need to use it. And that's honestly kind of unfortunate because that's a good rule to know. And I don't think I picked out any other problems that would allow me to demonstrate that. So I showed it to you anyways. Now, our next problem that we're going to be doing is number 8. So, big problem. So 8. Now number 8 gives us this monstrosity, x to the 5th minus 6x to the 4th plus 11x cubed plus 16x squared minus 50x plus 52 equals 0. And it says it wants us to solve for all roots, given that 2 of the roots are 1 plus I and 3 minus 2i. Well, luckily they gave us things that are conjugate pairs, because rationals and complex will come in conjugate pairs, which means that 1 minus I and 3 plus 2i are two of our other roots. Now, we can use that rule that we used in that first problem, problem 2, where if we have f of x, our initial function, is equal to d of x times all of the different roots, x minus r1, x minus r2, so on, to x minus r4, because we know that these are all 4 roots here, and then this d of x would be our 5th root because we have a degree of 5. So if we have 5 like this, we know that our final is going to be just an x minus r5, because it'll only be to a degree of 1 since we have 4 given to us, and then 5 total. So then how we would do that is divide this function here by all r1, r2, r3, r4, which would cancel out all of these when we go and divide. And when I say r1, r2, r3, r4, I mean x minus r1, x minus r2, x minus r3, and x minus r4. And then that would give us our 5th root. So let's go ahead and do that and stick to that standard. So first of all, how we would do that is try to first find what quadratic this and this would be by multiplying them together. So the actual root form of this, as we saw earlier, is x minus r, which means we're going to do x minus 1 plus I, and then x minus 1 minus I, and that's going to be our first double root. And the thing is, I'm going to multiply the conjugates together because then that would cancel out all i's. Now there's a shortcut for doing this. If we want to do the shortcut, it'll be multiply those two, and then these two, and then these two, and then ignore the i's except for multiplying them with one another. So you'll basically multiply everything together that isn't the i's, and then the i's only to one another. So you'll go like this, because otherwise it'll all cancel out. You'll get negative I, and then you'll get a positive I, and then you'll get a positive ix and a negative ix, which will just cancel out. So we'll go x squared minus now it's both minus 1, so we're going to get minus 2x, then 2 1s, so it'll be a plus 1, and then multiply the i's together. It would be negative I squared, which is just positive 1. So this here will be a plus 2. And then we'll do the same thing with the 3 minus and 3 plus 2i's. So we'll go x minus 3 minus 2i, and then x minus 3 plus 2i, and multiply those together. So we'll get the same rule that we did before. So x squared minus negative 3 times 2, because there's going to be 2 of them, so minus 6x. And then we'll do the 3's, which would be plus 9, and then we'll have negative 4i squared, which is the same as positive 4. So we'll have that there. Now, there are two ways we can go about this, and I'm going to do the second way I'm going to show. So the first way is to multiply these two together immediately to get a huge fourth degree number, and then divide everything by our initial, or divide our initial by that huge fourth degree. I'm not going to do that because the second way is to divide each individually. So then to go this whole thing divided by that, and then the answer of that divided by that. Because what that allows you to do is check your work twice in the middle, because obviously you're still doing it right if you get a remainder of 0. So you'll be checking your work twice as you go. But if you just multiply these out immediately, if you make a very small number or sign error, then you won't be able to check your work, and you'll come out with a huge nothing that has a remainder. And then that'll mean literally nothing to you. So I'm going to do that other way, where we take this whole thing and divide it by 1 at a time. So we'll go x fifth minus 6x to the fourth plus 11x cubed plus 16x squared minus 50x plus 52, all under. And then we're going to go x squared minus 2x plus 2. Doesn't matter which one you do first. But I'm going to do this one because it has smaller numbers first. So we're going to go x cubed because we need it to equal x to the fifth. So we're going to go like this, minus 2x to the fourth plus 2x cubed. And now I'm going to just do some math here, just some very long and drawn out math here. That I don't need to narrate every single part of. And then just remember you have to distribute that negative, hence how I got that 9x cubed minus 4x plus 8x cubed minus 8x squared minus everything, so then that would be a plus. We would have x cubed plus 24x squared minus 50x plus 52. Okay, and then this would be a plus x. So we'll have x cubed minus 2x squared plus 2x. Subtraction, distribute that subtraction sign and then do it. So 0, we'll have here 26x squared minus 52x plus 52. Then we'll multiply this whole thing by plus 26. So 26x squared minus 52x plus 52. Perfect. It's subtracting by the exact same thing, remainder 0. This is the first check answer. So we know that we did our math right up here, and we know that this is what it is divided by. So let's pull this over here, and we'll go x cubed minus 4x squared plus x plus 26, all divided by this one here, x squared minus 6x plus 13, instead of having to just divide by this whole nonsense again. So then we'll go x cubed minus 6x squared plus 13x, subtract, add that over, we get 2x squared, subtract that, we get negative 12x plus 26, so then we would go plus 2x squared minus 12x plus 26, exactly the same thing as before, 0. That's our second answer check that we know that we have a remainder of 0, which means this is our final here, which means our final, where we have all roots, is going to be 1 plus or minus I, 3 plus or minus 2I, and negative 2. We know it's a negative 2 because our whole answer is positive 2. And those would be our roots for this. And obviously you could just plug it into a calculator to check, but I have all the answers here, so I don't need to do that. Okay? Now we are going to do number 9. Okay, here we go. I'm going to erase all this now. Here we go. So number 9 says P of x equals x to the 4th plus 2x cubed minus x plus 6, and then d of x is equal to x squared plus 1. Find polynomials qx and rx. So I'll explain what that means in a minute. So px such that px is equal to d of x times q of x plus r of x. So, wow, that's complicated. So, if we don't know how the long division works, we can remember to ourselves that if we get a remainder at the end of our division, like let's just say for a minute, let's say we were dividing, let's say we were dividing 10 by 3. How it would work is we would say 3, 9, subtract here, 1, divide that, so we would go 3 plus 1/3. So we would go our remainder divided by our number, which means we're left with an answer plus a remainder, which is exactly what we would want up here. Except since we're not actually dividing it, it would still be 3 plus 1/3 all multiplied by 3. And that's what they mean by this dx, qx, and rx, is that would be our full thing. So we have that px, so we need to find polynomials qx and rx. So basically what we need to do is, in other words, it's asking us, we need to divide that by that, find what it equals to, and what the remainder is. So we'll go like this. I'm going to use a different color. X fourth plus 2x cubed minus x plus 6. Now, one thing really quick is before I even go on, I'm going to fill in a 0x squared minus x plus 6, because that will make my math check out. I'm going to do the same thing in the divisor, x squared plus 0x plus 1. That will make my math check out. If I don't do this, then I forget parts, and then our math doesn't work. So x squared, and then it also just doesn't line up, so this makes it line up. So x squared, we would go x fourth plus 0x cubed plus x squared. So we would go 2x cubed minus x squared minus x plus 6. Notice how that x squared term popped up seemingly out of nowhere. So now we will hit it again with a plus 2x. So we'll have 2x cubed plus 0x squared minus 2x, subtract, we'll have negative x squared plus x plus 6, and then we'll hit this with a negative 1. So then we'll go negative x squared plus 0x minus 1, subtract it over. Now remember, it said there was going to be a remainder, so it's perfectly fine that we'll have a remainder, x, and then it would be plus 7. So that means our qx is equal to this up here. Our remainder is equal to this here divided by that. So qx is equal to x squared plus 2x minus 1, and then rx is equal to x plus 7 divided by x squared plus 1. Now, if we wanted to follow this exact thing, we would have this Rx be just x plus 7, but just know that the actual remainder, if we wanted to add it up to the total thing, would be this x squared plus 1. Okay, where are we at in video length? 13 minutes, that's not bad. It's not bad. Now, the next one that we're going to do, which one did I write there? That's a 15. Ah, okay. That's not bad. So, 15 says, find a polynomial fx with leading coefficient 1. So, fx with leading coefficient 1, such that the equation fx equals 0 has the following roots and no others, with roots 2, 3i, and 1 plus rad 2. And this is of a multiplicity 1, this is of a multiplicity 3, and this is of a multiplicity 2. Okay, now this one is actually extremely difficult. So I will explain why it's extremely difficult, because it seems easy, but we want our leading coefficient to be 1, which means it might not be easy. Although it doesn't, it wants us to write our answer in this form. an x minus r1, so no, it's actually not going to be that difficult, x minus r2, x minus r3, or it's going to go x minus r2 and then dot 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 x minus r to the end, showing just how many it needs to go to get to that. So this is the form of the answer. So this actually isn't that bad. So what we want to do is this. So we are going to go f of x is equal to x minus, so multiplicity 1 over root of 2, so 2, and then we were going to go 3i, so to the third, so it would be x minus 3i to the third power for that many multiplicity, and then we were going to go 1, so x minus 1 plus rad 2 to the second. And then that is going to be our total thing for that. I'm going to just check that that is indeed the answer, because it is extremely complicated how that works. So I'm just very quickly going to verify that it is indeed that. Yep, that is the answer. And then that an, we don't really even need to mention it, because that's just saying there may be a coefficient that comes before it. So this here is our answer. So I thought it was going to be super difficult, because sometimes when they say this, they say you can only have integer numbers or no complex numbers, in which case you have to FOIL this whole thing and then multiply it by certain numbers to make it, multiply by certain seemingly random numbers to make it all check out. And then it didn't say that. So that's very good. So now, which was the next problem that I said that I wanted to do? Okay. Next problem was 17, which I believe... okay. I'm going to end the video for time's sake. So number 17 asks us to write 3 plus I divided by 1 minus 4i in the standard complex number form a plus bi. So this one shouldn't be too hard, as long as we remember one rule about how complex numbers works. So if we want to get a complex number out of the denominator, we have to multiply it by its conjugate. So the conjugate of this one would be the flipped sign here of the bottom term. So we would multiply 3 plus I over 1 minus 4I by 1 plus 4I. 1 plus 4I, which is equal to, we would just go ahead and simplify this all out. So let's start with the top. We'll go 3 plus, I'm going to write the dots so I know what I've already FOILed, 12I plus I plus 4I squared. Okay. And then we get 1, 1, so 1. The i's will cancel, so we only have to multiply the separate parts, hence why we did a conjugate pair in the first place. So 4, so negative 16I squared. And then we'll go ahead and simplify this again to 4I squared is negative 4. So we will do negative 1 plus 13I all over 1 minus 16I squared. So I squared would be negative 1. So that would be 1 plus 16. So all over 17, which means that our answer will be negative 1 over 17 plus 13 over 17I. And that is our answer in a plus bi form. Now, we will go on to probably the hardest things in this chapter, partial fraction decompositions. So if you don't know what a partial fraction decomposition is, it's a setup, it's like a tee-up for how calculus will work, because it's way easier to do calculus work on rational problems that have been put into their partial fraction decomposition forms. So our first one we're going to do is 19. So 19 has 1 over x third minus x squared plus 3x plus 3, or 3x minus 3. All right, now the first step to solving a partial fraction decomposition is finding what our bottom terms roots are. That's the first step. So go ahead and try to do that without me, but I'm going to start now on that. So I'm going to use a different color. So we have x cubed minus x squared plus 3x minus 3. So if you don't realize, this can be factored by grouping. So we'll pull out an x squared, x minus 1, pull out a 3 here, and then we'll do our normal nonsense here. Okay. So these are our two bottom roots. So what I'm going to do is just go like this with them. Now, if you remember how partial fraction decompositions work, we basically have to put this into this form. A over root 1 plus b over root 2, or rather the expression that would lead us to root 2, because we can't have complex numbers. And then it would go all the way until we get to x root n. Now, of course, we only have two roots here, so we only have to go to just this a plus b step. So we are going to set this up as a. So actually, you know what? I'm going to rewrite the whole thing as well, because that would make it easier. 1 over x minus 1, x squared plus 3 is equal to a over x minus 1 plus b over x squared plus 3. So now what we can do is multiply. Oh, you know what? This here is not just a b. It is a bx plus c. Normally, it stays this a, x minus 1, but it turns into a bx plus c, so it'll basically turn into a thing with a degree of 1 less than the root it is. So here the degree is 1, so along the x's, this one will have a degree of 0. This one here is a degree of 2, so this one here will have a degree of 1. So it will turn into an x plus something. And that's why we will do that there. So if, for instance, our root was like x cubed plus 3, then what would be at the top would be like a b squared or a bx squared plus cx plus d or something like that. Some nonsense like that. But we would never split this up into its complex form because that's just not how you would set up a partial fraction decomposition. So now what we'll do is multiply everything by x minus 1 and x squared plus 3, because then that will get everything out of the fractions. So we'll go 1 is equal to, the x minus 1's cancel here, so it'll just be a times x squared plus 3, and then we'll have plus x minus 1 plus bx plus c, so we'll have x minus 1 bx plus c, since the x squared plus 3 will cancel out. Now, there are two ways to go about this. I'm going to use the first one to display the first rule, which is, I forget the actual name for it, but it's a form of pairing. So we are going to simplify all of this out. We're going to go 1 is equal to ax squared plus 3a plus, and then FOIL this out. So we'll get bx squared minus, so we're going to get bx squared plus cx minus bx minus c. Okay, and now if you can take a guess at where I'm about to go, it's very important that you understand how this works. So what I'm going to do is take this and group it by the degree of this x value. So 1 is equal to ax squared plus bx squared. And then I'm going to take the singular x's now, so plus cx minus bx. So I'm going to go like this. You know what? I'm not going to put them in parentheses because I don't need to. And then I'm going to take the single values, plus 3a minus c. If you'll notice, our answer has no x squared values and also no x values, only 3a minus c values. So we can get what we learned from chapter 11 about systems of equations to set up a system for this. So we know that a plus b has to equal 0 because there is no 0x squared over here. So we know a plus b equals 0 because the only way we can get these two to cancel out. We know that c minus b is equal to 0. And if you see really quickly, what I did was basically x squared a plus b to represent this. Here I went x, c minus b, and then here I don't need to do much. And then we know that 3a minus c is equal to 1. So let's go ahead and try to solve this system. So we know here that a plus b is equal to 0, so we can also simplify c is equal to b based on that second equation. We can plug in a c for that, so a plus c equals 0, 3a minus c equals 1. So that's like a subset that we can gather, and then we can go ahead and try to solve for this. Hopefully you can still see what I'm doing. Yes, you can. So this here is a subset of that. So if I wanted to cancel this out again, I could do one thing like this, and I could say a is equal to negative c, and then 3a, or I could go negative c is equal to 3a minus 1, or no, 1 minus 3a. So what I'm doing is getting them both equal to the same thing, so that way I can then set both of them equal to one another. So a is equal to 1 minus 3a. Add that over, we get 4a is equal to 1, so a is equal to 1 over 4. So now we know a is equal to 1 over 4. So if a is equal to 1 over 4, then that means b has to be equal to negative 1 over 4, so that those can add to equal 0. And then if c minus b equals 0, that means c is also equal to 1 over 4. So because 1 over 4 plus, so this has to be negative 1 over 4. So if you see what I just did there, so c, negative 1 over 4 plus 1 over 4, because these two negatives will turn into a plus, has to be equal to 0. And then we'll verify it by plugging it in here. So 3a minus c has to be equal to 1. So 3a, so 3/4 plus 1/4, because the two negatives will turn into a plus, is equal to 1. Yes, it is. These are our three ABC values. So now we'll plug this into the top one over here. So we'll have 1/4 x minus 1 plus, now that bx minus c would be negative 1/4 x plus, so minus 1/4 all over x squared plus 3. That there is our partial fraction decomposition for all of this. Now, the most crucial step is figuring out what I did to go from here to there. And when I went from here to there and trying to solve the a's, b's, and c's, I noticed that there are no x squareds here, so I know that the coefficients must add up to 0. I know there are no singular x's here, so the coefficients on the x's had to equal 0. And I know that of the ones that had 0, they must add to equal the number 1. And then I just solved the system that comes out of that. And then I just did some math here to solve this system. Now, you could have gone 50 different directions with that math, but this is the direction I went to try to then solve that system. Where are we at on time? 12 minutes. Okay. Hopefully, I'll be able to get through number 20 by then. I should be able to get through that before 30 minutes, because that's when the file size becomes way too big. We're all good? Yep, next problem is 20. Let's do it. Twenty states, oh no, 4x squared minus 15x plus 20 all over x cubed minus 4x squared plus 4x, and that's it. Partial fraction decomposition for that. So we know our partial fraction decomposition form is a is equal to root 1, which is equal to root 2, which is equal to root 3, that nonsense there. So then we can go there and solve for everything. So we know we have to find the bottom roots as our first step for partial fraction decompositions. So we'll pull an x out of this whole thing, so x squared minus 4x plus 4. If you'll notice that that's a perfect square, that's because it is. X minus 2 squared. So that is our roots. Now, there's a secret that comes with having the squared forms. If you have the squared forms, what you're going to do when setting up your partial fraction decomposition total is this. First, I'm going to write the whole thing again, but with this simplified form down here. 4x squared minus 15x plus 20 all over x minus 2 squared. So when you go to do your A's, B's, and C's, so you're going to now have A over X plus B over, now before I go about this, I'm going to show you how this will work. There's a rule about how partial fraction decompositions work that I would assume you would learn in calculus that says that when you go to try to form partial fraction decompositions with this x minus 2 term, you will first use its only multiplicity 1 form, and then you will use its multiplicity 2 form. So if this here was a multiplicity of 3, you would go x minus 2 squared, x minus 2 cubed. And that is just how they work. And then your solution will involve this x minus 2 squared here. And then this will stay as just a c because that's part of this here. And that's just how that works. It's as simple as that. And why it works like that, I would assume, is I actually looked up how it works like that, and it involves insane linear algebra, which is like beyond calculus. So very difficult stuff. Or it's some very difficult rules. So we're going to multiply everything by this bottom term here. So we're going to get 4x squared minus 15x plus 20 is equal to, multiplying by this here, we're going to get both. We're going to have x minus 2 squared, so we're going to get a x minus 2 squared plus b. This b is going to be multiplied by both an x and an x minus 2, since one of the x minus 2's will be canceled out by that. And then we'll get a c that will just have an x attached to it. Okay, now we're going to do our second type of rule. If you saw the first one in 19, this is going to be our second one. We're going to do we're going to plug in useful numbers here to try to solve for it. So plugging in useful numbers involves plugging in random numbers for x, but not random numbers that would help us solve the total problem. And I'm going to use the color brown for this instead, a different brown than that one. So there are some useful values here that will allow us to eliminate all variables except for one. If you can think of those two numbers now, because sometimes there's 2, sometimes there's 3, sometimes it just depends. If you can think of all of those numbers now, I encourage you to pause the video and try to do it. So our numbers are going to be the number 0 and the number 2. Those are the numbers we're going to plug in for x. That's because if we plug in 0, it would eliminate the b and the c, because then it would be multiplying by 0. If we plug in 2, it would eliminate the a and the b, so that would leave us with just c. And then when we solve for a and c, we'll just plug in those values at the very end to solve for b, while plugging in a random number for x, so that we can solve for b once we have a and c. So you'll see how I'm about to go about this. So first I'm going to plug in with 0. So I'm going to plug in the whole thing with 0. So 4, 0 squared minus 15, 0 plus 20 is equal to, plugging in the whole thing for 0, a 0 minus 2, so negative 2 squared, and then we know that these will cancel, so I'm just not even going to bother with them. So we have 20 is equal to 4a, so a is equal to 5. Okay, now I'm going to bubble this. And now we're going to go and solve for c by plugging in 2. So we're going to have 4, 2 squared minus 15, 2 plus 20 is equal to, if we plug in a 2 here, that'll make it a 0. Plug in a 2 here, that'll make it a 0. Plug in a 2 here, that won't make it a 0. So we're going to have 2, not a, we're going to have c now. So then we'll simplify this side. We'll go 2 squared, so 16 minus 30 plus 20 is equal to 2c. Simplify it down again. Negative 30 plus 20 is negative 10. So then we'll have 6 is equal to 2c. C is equal to 3. What is my mom watching right now? I don't know if you can hear it, but I'm going to shut my door. I just hear this like heavenly, oh, and I'm like, no, stop. I'm recording a video. So now we have c is equal to 3. Now what we're going to do is plug in a random number for x that isn't 0 or 2, so that we can be left with just b, because we know a and c now, so let's just plug in a and c and then solve for b. So let's plug in a 1 for x, because 1s are very simple to deal with, and then we'll also plug in a and c. So if we plug in 1 for x, we'll be left with a 4 and then 1 squared, so minus 15 plus 20, and then is equal to 5 times 1 minus 2 is negative 1 squared is just 1, so this would be just 5, plus b times 1 times -1 plus c, so 3 times 1 is just 3. So then we'll go about and solve this. So that would be 9 is equal to 8 minus b. So add that b over, subtract that 9 over. B is equal to -1. So now we'll plug this into our total. We have a, so 5 over x plus, so that would actually be a minus 1 over x minus 2. Sometimes you'll see in the answer sheet this will be a plus and that'll be a minus, but I prefer to make the whole thing minus. And then we'll have plus 3 over x minus 2 squared. And that will be the total of our partial fraction decomposition for number 20. And we are done with the review for chapter 13. Woo! Oh, God.